Okay, welcome to lecture 10.5. All right, now, uh, here's what we're going to do. We're going to use the Signorino model, and instead of that, U of SQ1, or excuse me, U of U1 of SQ, and U1 of W1, and so on. Where before I said we just treated those utility terms as like it was a number that we were given. It was like payoffs in an experiment. Okay, we're not going to do that anymore. Okay, now instead, we're going to assume that those utilities are functions of independent variables. Okay, so this is the innovation that Signorino has done. He's saying, okay, look, Kelvin Pelfrey, so far all they've done is just looked at it for experimental data where you're given the payoffs, you're given the seen payoffs. Now I'm going to assume we don't know the seen payoffs. It's just a coefficient times an independent variable. Okay, it's going to be harder to try to say what those seen payoffs are. Okay, so to do that, okay, first let's call it independent variables. Okay, first thing, mi equals i's, state i's, military capabilities. And I think the easiest way to interpret that is just to think of them as, I guess it's assets defined in dollars. Now, I guess it's hard to do because soldiers, how do you define the dollar value of a soldier? Assume there's a way. There's some way. A soldier is worth uh, $500,000 worth of equipment, something like that. Okay, so MI, it's in dollars. All right, AI is A sub I equals um, I's domestic assets. Maybe I should have said other assets, non-military assets, and this is wealth that is not in the military. And where we're going is that if the countries go to war and country I loses AI. AI that is given to the state that wins. All right. DIJ equals um, indicator if I and J are democracies. Okay, so in the international relations literature, there's this huge empirical regularity called uh, the democratic peace. That if two countries are democracies, I think there's like zero cases in the last 100 years where they've gone to war with each other, maybe forever. I don't know. It's like this huge empirical regularity. And so Kurt saying, okay, we got to somehow account for that. So DIJ is going to be an indicator. So the data is pairs of countries. And so if the two countries, I and J, are both democracies, then DIJ equals 1, 0 otherwise. Okay. And then PI equals, I guess if we only have two countries, I's probability of winning war with the other country. Okay, and we're about to we're going to simulate some data, and we're going to assume there's only two countries, and PI. So I told you that's an independent variable, and what Signorino asserts is that that has a very simple form. It's just if I and J are the two countries, it's MI divided by MI plus MJ. Okay. So it's the percent of the total military assets that you own if you're a country I. And that we're going to assume that it equals your probability of winning the war. Very simple assumption to make. Okay. Next, given that, all right. Okay, country I's. Okay, UISQ just equals beta D times DIJ. Okay, all right, here we go. So, country I's utility from just having the status quo, keeping the peace, no conflict, no capitulation, no war, is just a parameter, beta D, times that indicator, whether you have a democratic peace or not. So see where he's going on this. He's going to say the countries with if both countries have a democratic peace, they get a higher utility from peace. If both countries are a democracy, they get a higher utility for peace. Okay, maybe a little ad hoc, but fits the data, fits that democratic peace regularity. Okay, UI of CI. All right, so if I'm country I and I capitulate, so if I'm country one and country one capitulates, what is my utility? It is negative beta A. You know what? Signorino puts a I. I guess the two countries can have a different beta. I might have made them the same beta. But that's multiplied by AI. All right, so if you capitulate, you lose all your non-military assets, and so the negative utility, negative beta, sub A times that. All right, UI CJ. Let's see. U sub I CJ. Darn, you know what? My notes, I put a negative sign in front of it. I don't think that's right. I think you shouldn't have a negative sign there. So, but that I'm not going to put the negative sign. So this equals just beta. Darn it. Kurt puts a J. Beta A. The other guy's J times AJ. It's not going to matter that much. Okay. Because it turns out we're not quite going to estimate these things. It doesn't matter that much. I'll explain. It'll become more clear later. But anyway, for now, I'll just say it's beta. It's possibly a different beta than that beta. And it's multiplied by the times the other guy's assets. And I didn't put a negative sign because you take them. You steal if the other guy capitulates, you steal his assets. Okay. And then UI. All right. So UI of, okay, Kurt just calls it war. So we're going to assume it's the same, whether the other guy starts it or not. Whether you start it or the other guy starts it, you're going to have the same utility. And we're going to assume that it's we're going to take your expected utility from war. So when you decide whether to go to war or not, you don't know whether you're going to win, but you have this probability that you'll win. So we're going to have your expectation of winning, which is a weighted average of PI times your benefits if you win, times 1 minus PI, your cost if you lose. So this is going to be pi I think it's beta. Yeah, beta A J times AJ. So the probability if you win, you get this term, this beta A sub J times the assets of the other guy. Okay. So you steal his assets, and then if you lose, so 1 minus pi, so weighted times, what happens if you lose? Negative beta AI, you lose your own assets, minus beta M I. You also lose your military assets. Okay. All right. So those are the utility functions. Okay. So now remember, the P's are data. That's right. It's just mi divided by mi plus mj. So that pi is not estimated. That's data. Okay. So note first, every case where we have an independent variable, it's multiplied by beta. Okay. I guess here what's the interaction term? Pi times AI times, okay, times the beta. All right. Okay. Keep that in mind. All right. Now, okay. So now, what would happen if we substituted these things? Let's see. Let me use P4. If we substituted these terms into our likelihood function. Okay, now recall, okay, I think I already erased the board. Our likelihood function is just going to be a function of those P sub 1s, Q sub 2s, Q sub 3, P sub 4s, those terms. Okay, so all we got to do is we take one of those P or Q terms. Okay, it's going to look something like this. It's going to involve an e to the lambda times one of these utility terms. Okay, now all we would have to do is start substituting in for these utility terms. Okay, before I said, what if this is an experiment? It's like we had a number here. Now we don't. Now instead we have U1 of W2. All right, so U1 of W2, what is that going to be? Well, it's going to be this term. So W1 equals U1 of W2. So it's going to be P1 times beta A times A2. You get the other guy's assets. Plus 1 minus P I times negative beta A1. Here in this case, I lose my own assets times M1. Okay, those are all independent variables. All right. Now, we're going to multiply all of that times lambda right here, okay? So that's what we would substitute. So the numerator for P4 would just be e to the lambda times U1 times all of that stuff. Okay, now, here's what I want you to notice next. Okay, let me do that. Let's suppose that we put in that numerator and we multiplied all that by lambda. Okay, so let's do brace. Okay, so it's lambda times all of that. All right. Now, if we simplified this term, so we use the distributive property, lambda times pi times a beta times a ai, okay, what we're going to get is a lambda times beta times an interaction of our two independent variables, pi times ai. In this case, we're going to have lambda times negative beta times a1, which is data, times 1 minus pi, which is also data, okay? Something similar here, okay? Now, here's the key thing to notice. Every time when we write out this P4, this would be the numerator, every time that we wrote beta, there's going to be a lambda multiplied by it, okay? Notice here, this term's going to have a lambda beta A. Term here is going to be a lambda beta A1. That's lambda beta A2. There's lambda times beta M1. Okay. All right. So every time, I'll say that again. In P4, in the numerator, we're going to have e to some stuff. In that stuff, we're going to have some betas. Every place there's a beta, it's going to be multiplied by lambda, okay? Same thing is going to happen in the denominator. It's going to be two terms, e to some stuff, and every time we have a beta, it's going to be multiplied by lambda. Okay, so that was, okay, that we talked about P4. Okay, same thing is going to happen with Q3. We're going to have e to the lambda times u2. If we write out that u sub 2 of w1, same thing's going to happen. In this stuff, every time there's a beta, it's going to be multiplied by lambda. Same thing's going to be true with this term. E to some stuff. Every time there's we do the distributive property, every time we're going to see a beta, it's going to be multiplied by lambda. Same thing's going to be true with 1 minus Q2. Same thing's going to be true with the P1s, okay? Every one of those P or Q terms, in every one of those P or Q terms, every time you see a beta, it's going to be multiplied by lambda, okay? So what that means is you're going to have things like lambda times beta A1, okay? You're going to have another case, lambda times beta M2, okay? Again, every time you have a beta, you're going to have a lambda multiplied by it. Here's what that means. The lambdas and the betas are not identified. Here's why. You just multiply all the betas by some constant, say 2.7, whatever. Pick some constant. Divide the lambda by that same constant. It's not going to change anything. Every one of those terms is going to remain the same. Okay? Once again, if you multiply all the betas by some constant, divide the lambda by that same constant, no term is going to change. So none of the P terms or any of the Q terms are going to change. So that means the likelihood function is not going to change. And so that means the lambdas and the betas are not identified. Okay. What does Signorino do? He says, well, this is, same thing happens in a probit. A lot of cases. We have same thing, something similar happened with the Levitt-Porter paper. The way we'll solve that is we're just going to set lambda equal to 1. Okay. So now you have to be careful. Some people are saying, oh, you're making an assumption. Lambda represents the rationality parameter. And Kurt says, well, not really, okay? In this case, because we're estimating the betas, really the rationality is lambda times the beta, and we're not really saying anything about the rationality when we set that lambda equal to 1. If it were the case that the actors are super rational, which in McKelvey-Palfrey means lambda equals infinity. Well, that would just cause all the betas to be infinity, okay? Or if they're super irrational, so McKelvey-Palfrey case where lambda equals 0, okay? All that would do is cause all the betas to be 0, okay? So Kurt Signorino rightly says, really we're not imposing any kind of an empirical constraint, okay, by setting this lambda equals 1. The betas can take up the slack, okay? So given that, all right, we're going to set lambda equal to 1. All right. Okay, then from there, okay, if we have lambda equals 1, we're going to substitute the betas times those independent variables for all those utility terms, the seen utility terms. We could do that. We could rewrite the likelihood function, okay? Once we've done that, then we have those betas. We have the beta A1, beta A2, beta M1, beta M2. I think those were, and then beta D. So I think there's only 5 betas now to estimate. So now just stick those in, rewrite the likelihood function, set lambda equal to 1. There's 5 betas, okay? In theory, we could maximize that. And that we could estimate those 5 betas, okay? So that's where we are now, okay? So Signorino has described, now he actually hasn't gotten data yet, okay? But he's just described how in theory, we could observe some of these things, the assets of countries, the military assets of countries, whether 2 countries have are both democracies or not. Those things are all observable. And so in theory, we could estimate those 5 betas. Okay, so I will end there for this segment. Okay, when I come back, we're going to talk about how Signorino does that. He actually, it's actually simulated data. He doesn't actually get real data from countries, but it's not the same as experimental data, okay? These are a case where he's going to make up independent variables and then he's going to estimate those betas. And that's something pretty remarkable. That, remember, he was a grad student when he did this. So this is a real innovation, an extension, I would call it, and a contribution beyond what just McKelvey and Palfrey have done. Okay, we'll talk about that in the next segment.